Okay, it's about time to start. Let's begin. Okay, so today I'm going to cover binary, decimal, and hex, basically number systems. I might talk about flowcharts if I have some time at the end, but I feel like I should start doing the actual content and then we'll get back to flowcharts in a little bit. So, hello. What are these three things? So that's a good question. So, basically, I guess the way to start is, we usually have 10 fingers. Right? It makes it easy for us to count from, say, 0 up to 9, or maybe you would say 1 to 10. And so, really, that's 95% of the reason that we have a base 10 system, right? So, we usually work in base 10. And the reason why is because we have, 10 fingers, and so we can kind of count. And so what does it mean to be in base 10? So what is a base, right? When we say base 10, what do we mean? What do we mean, right? And so the answer to that is that basically what we mean is there are slots and there are digits, right? And so basically you'll have a certain number of slots, say 3 slots like this for now. Okay, that really doesn't want to do. And so if we have, say, 3 slots, and we put 3 numbers in those slots, so we have those digits from 0 to 9. So our digits are 0 to 9. You can put like a 3, say a 4, and then a 7, right? So what does this mean to us, right? So what this means to us is that we would say that there's like a 7 in the ones place, and then we'd say there's a 4 in the tens place, and then we would say there's a 3 in the hundreds place, right? And so the idea here is that basically whatever our base is, each slot goes up by a factor of that base. So for instance, if this slot means 10, right? It's 4 times 10, then this slot is 3 times 10 times 10, or alternatively 3 times 100, right? And so that's what these slots mean. Basically what this means is that, you end up with something like this. You end up with 7, 4 times 10, and 3 times 10 times 10, and if you add those all together, right, then what you're going to get is the decimal answer, right? Okay, so that's basically breaking a number apart in decimal and putting it back together, right? It's basically saying that every one of these slots that we create is a place, and that place increases our power of the base by 1, right? So you start, the power of the base here is 0, right? So the power, this is 10 to the 0, right? Which is equal to 1. And the reason why you have 10 to the 0 is because 10 to the 0 is equal to 1 times 7, so you can get 7. And so this is a way to represent numbers, right, that are, bigger than our base, right, by just saying, okay, well, if it's bigger than the base, then put all the overflow into here, and if something overflows, then put it into here. If something overflows, then put it in the next slot, etc., etc. Okay, so, all of this is just decimal, and so you might be saying, okay, well, I've, since the beginning of time, right, I've been taught the decimal system, and so I vaguely understand all the things that you're saying here, right? You understand that when you're in base 10, your digits are 0 to 9, there's 10 such digits, and you represent numbers by putting them basically in slots. Okay, so that's a good thing. Okay, so how does binary work, right? Right, so binary is actually very similar to decimal. So is hex, really, but let's stick with binary for now. So why is binary similar to decimal? Why are they similar? And how are they different, right? So they're similar in the fact that places represent powers of the base. And of course, I haven't told you what the base is yet. You all kind of are screaming out what the base is going to be. Right, places represent the powers of the base. And what else is similar? Each slot has just one digit, but I'm putting digit in a quotation because the D in digit usually stands for 10, so normally we'll call a binary digit a bit, right? So that's the way to say it, like a binary digit gets kind of mushed into the word bit. And so how are they different, right? And you can represent any number in binary or in any base, right? So it doesn't matter if you're representing a number in base 2 or base 10 or technically in base 3 or base 5 or base 17. You can represent any number in any base. So that's how all these number systems are similar. But how are they different? Well, this is basically how it's different. Instead of the base equals 10 for decimal, the base is equal to 2 for binary. And that's it. That's the one main difference. And the other difference is that because the base is 2 instead of 10, you can't have, let's look at our digits. Our digits are equal to 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. But most of these are not possible because you would say, okay, the base is the maximum allowable thing, so you can't, and you notice how here, our base is actually 1, 0, right? So it's 1 in the tens place and 0 in the ones place. So you can't actually represent the base in its own number system, right? In a single digit. Anyway, so here we have 0, which is okay. We have 1, which is okay. 2 is too big, right? 3 is too big. 4 is too big. All of these are too big, right? So the only bits that we need are 0 and 1, right? So that's all we need. Now, okay, so this leads to a bunch of different questions, right? If you can evaluate, represent any number in any base, here's what we basically want to do. We want to convert a binary number to a decimal number. And then we also want to convert a decimal number to a binary number. Okay, so those are the two directions that we want to go. And then when we learn hex, we'll convert from binary to hex, decimal to binary, all the different ways. But for now, let's just do decimal to binary. And let me show you how to do it. So for instance here, let's represent a binary number. So a binary number is going to be a bunch of zeros and ones. So let me just write down like something like this. Well, let's start off with something simpler. Here's 101. Okay? Now in decimal, this is 101. And in binary, It's what? So here's the question. So how do we evaluate this as a number? So the answer is what we're going to do. And so this is the conversion, really. Really, I'm doing this binary number to decimal number conversion. And it's really because it's the easiest, it's one of the easier ways to do it. So you know that this digit here, right, this is in the ones place. Yep, this is the ones place. And then this is no longer the tens place, right? This is the twos place. And then finally here, this is the fours place, right? And so the reason what we're going to do here is what we're going to do is we're going to take the ones place times 2 to the 0, right? Plus 0 times 2 to the 1, plus 1 times 2 to the 2, right? And so what that's going to end up being, and let's actually make that in LaTeX so it's a little bit prettier. But while I'm making this in LaTeX, right? What am I going to do while I'm making this in LaTeX? That's a good question. I got distracted by LaTexing. Right, let's evaluate. So 1 times 1 plus 0 times anything plus 1 times 4, right? So the point here is that this is just equal to 1 plus 4, which is equal to 5. But this is in decimal, right? This is, I'll write a D after these to indicate decimal, right? So basically all of these calculations are now in decimal, right? This is in binary, and after here, all of this stuff is in decimal. Okay. And so that's how you would convert from a binary number into a decimal number, right? You basically just keep taking powers until you get to the top of the number, and then you just add it all together, and that's what you're going to get. So let's let LaTeX render for just a second. Program is hanging because LaTeX is doing its thing. Okay, here we go. There we are. So that's a little bit prettier notation. It's a little bit better, right? Okay, but it's the same stuff, it's just written in a nicer format. Okay, so let's do another binary number, right? And before I do any more binary, let's talk about the motivation here. Like, why do we care about binary, right? And so the answer is really like, the answer is that computers think in binary, right? But that's like a stupid thing to say. What we really mean by that is that computers are limited to basically two states, right? On and off, right? So when you learn about circuitry and when you learn about gates and stuff like that, like most processors operate somewhere between like 1.1, maybe 1.6 volts, and you know, RAM sometimes operates maybe 5 volts, hard drives operate at 12 volts, but no matter what the voltage is, either a circuit is on or it's not, right? The problem is that if you wanted to do some kind of analog computer that detected like multiple voltages, that is not impossible, but unfortunately that's not digital computing. So the reason why it's not digital computing is because you would be able to detect all kinds of different voltages between the 0 voltage state and the on voltage state, which is usually like, let's just say 5 volts or 3.3 volts or 1.6 volts or something like that. So that's why we use binary, because wires can either carry current or not, and they can either have a voltage or the voltage is 0. And basically the point is that that is why binary exists. It exists because of how computers are built, right? Computers understand on-off states, and that's basically all they really understand, right? Every piece of RAM, every bit of memory on a computer is storing everything in quote-unquote zeros and ones, right? But really, it's storing voltages, right? Or maybe, I guess it could be storing voltages, currents, some kind of electricity, right? It's doing something electrical. Or maybe even magnetic. Right? And so like a hard drive is storing things magnetically, other things are doing things electrically, but either way, either there's a signal or there's not a signal. And so that's why 0 basically translates to there is no voltage, there is no signal, there is no magnetic flow, or 1 translates to there is some kind of voltage on that line, right? And so that's exactly why we do binary, because computers, it's really basically understanding how computers work, right? And so that's the point. Okay, so let's make some more binary numbers and convert it into decimal. Yeah, basically 1 is true or on, and 0 is usually false or off, right? So that's kind of right. So will you always be told if a number is in binary? The answer is yes, because of this joke. So here's the joke. You don't have to laugh. And they always say there are 2 kinds of people. Those who understand binary and those who don't, right? And now, of course, you would say, oh, well, I get it now, because this is really 10b, right? 10 in binary, which is equal to, and of course, saying 10b is a little bit misleading. What we really mean is the number 2, right? The actual number is 2, right? But here, 1 0 in binary represents 2 to the power 1 plus 0, right? 0 times 2 to the power 0. So it represents 2, right? And so that's the joke. And so the point here is that the joke, obviously, and this is kind of the idea, the joke relies on not distinguishing the base that you're in. So oftentimes you'll see something like this. In Python, when you write binary, you use the prefix 0b before the number. Okay? And the reason why you do this, and let's pull up a Python interpreter so that maybe I can show you this. That would be a not terrible idea. Let's make a Python file, binary, decimal, hex. Change the font size. There we go. So you can say a number is equal to, say, 0b, 101010, right? But here's the thing. When you print out this number, watch what happens. Watch what Python does to this number. It just prints out exactly the decimal number. And so the thing is that Python can't remember whether you told it the number in hex, decimal, or binary, right? It always stores it in binary, and it displays it in decimal. And that's how it works, right? So basically, if you ever want to convert a number really quickly and you have a Python interpreter, this is the way to do it. If I ever ask you, like, what's a number in binary, the answer is you just take 0b and then you type the number in binary and then you just print it out, right? But let's actually try to understand why this is 42 rather than just saying, oh, it's 42 and being done with it, right? So why is this 42? And so the reason is because it is, and what I usually do is I usually start at this end and I'll say, okay, this is 1, and so then I say plus 2. Right, we don't add the 1, we add 2. We don't add 4, but we add 8. We add, well, so the answer is, remember, it always stores every single number in binary. So the real question that you want to ask is, can you display any number in binary using, using this? And the answer is yes, and let me show you that in just a second. So here, this is 2, 4, and then this is 8. this part is 16, and this one is 32, right? So overall, this is equal to 42, right? Cool. Let's do another few numbers. Let's say, let's look at the binary number 11111111, right? And the reason why I want to look at this binary number is that I want to show you something about binary numbers, and that is that you're almost proving the geometric series formula a little bit here. But anyway, let me just show you. So here, this is going to be 1 plus 2, right, plus 4 plus 8. And so this is 1, 2, 4, 8, and then we got 16, 32, 64, 128, and then 256. So plus 16 plus 32 plus 64 plus 128 plus 256. So as it turns out, this is going to be equal to what? 511. And I didn't just do that in my head. Well, I kind of did, but I didn't. The trick that I did was I said it's equal to basically it's equal to 2 to the 9th minus 1, which is equal to 512 minus 1. So anyway, but the point is that you don't need to have that trick memorized. I just did that for the sake of convenience. The point is that basically, if everything is ones, then you will just add up every single power of 2 up till that point. And let's just double check to make sure I'm actually correct, because it's always possible that I've said something horribly wrong, and 1 plus 2 plus 4 plus 8 plus 16, 32, nope, I actually plugged into the calculator wrong. 64, 128, 256, there we go. So here we go, 511. I didn't screw up. So, okay, cool. So let's do some more, and then I'll show you how to convert back. Let's do maybe 2 more examples of how to convert to decimals, or I'm sorry, yeah, how to convert to decimal from binary. So say 1101, 1101, something like this, okay? And you notice that I sometimes put spaces between each 4 bits, and the reason why I do that is it's purely for, what should I say, illustration, ease of reading. I promise you that the problem with binary numbers, and the reason why we invented hex, is to deal with the fact that binary numbers they're not great, right? Because, to represent 512, how many bits do you need? You need 9 bits, right? Whereas with, actually you'd need 10 bits to represent 512. You need 9 bits to represent 511. So the problem here is that it's hard to read these things, right? Because if I actually did like a number that was like 532,817 in decimal, and then converted that into binary, that's a lot of bits, right? So anyway, let me show you. Let's actually calculate this number. Let's do 2 more calculations here, and then let's do some hex calculations. I'm sorry. Let's do the binary to decimal calculations, and then move on to hex. So here you'll do 1 plus no 2, $, I guess, 4 plus 8 plus 16, not 32, and 64 plus 128. So I don't know what that number is. I guess I could calculate it. Can I do it in my head? Isn't that like 192 plus 20? So that's what? 112 plus 8, 120, or 220 plus 1, 221. I think. Let's double check. Yep, 221. Okay. And let's do one last one, right? So let's do, what's a good one? I mean, I don't know that there's any good or bad ones, really. And sometimes, I guess this is the last thing I'll say about binary before we start doing the conversion of decimal into binary, which is actually a little bit more difficult than the reverse direction. Sometimes you'll see things blocked up in 4s, and there might be actually some leading zeros like this. It's like if I wrote a number like 00128 or 00 like 3284, right? Those leading zeros, you can ignore them, but in binary sometimes we write them just so that everything is clustered in groups of 4. So if we do something like 0110, 1100, 0101, or okay, 0101, I'll stick with that. So we already know that this one is 5, right? Because 1 plus 4 is 5. The next one is what? So the next one is, so as a number, this is 12, right? If you just looked at this number in binary, this is 12 because it's, 4 plus 8? But if you look at it in the next spaces here, it's actually going to be what? It's going to be, this is 8, and then 16, 32, 64, 128. So you can, there's two things you can do. You can either multiply 12 times 16, and push it up in the digit, I guess the bits, right? Or you can do it another way. You can just say 16, 32, and then 64 plus 128. And let's hope that I'm not wrong, right? 16 times 12, yep. 64 plus 128, yep. Okay. So this next set is 128, or I'm sorry, 192 overall. And in the end, we're just going to add these three numbers. And then here we have 011, or I should say 0110. And how are we going to read that? We're going to read that as 0110. So this is in the 128th place, so this will be 256, 512, 1024, and 2048. Which ones do we have? We have the 512 place, and we have the, whoa, I don't know how I zoomed so effectively. I think I did, crap. Okay, 512 plus 1024 is equal to whatever it's equal to, I guess, what, 1536. And then the thing is that we have all three of these numbers, so we then just add them all together, right? Which will get us to, well, I have no idea what it'll get us to, but it'll get us to 1536 plus 192 plus 5. So I guess 1733 in decimal, right? So that's nice. You kind of see, though, how inefficient binary is for storing things, at least on paper. In a computer, I guess it's not terribly inefficient because I don't know a better way to do it, but, well, I guess it would always be better to have more storage space per bit, like if you could have like a quit where it had 4 states rather than just 2, right? But anyway, currently, at least with current digital computers, we're not talking about quantum computers, just digital computers. We still have binary, still have bits and all that stuff. Okay, so now we've done that, let's convert back, right? From binary to decimal, okay? Or, no, that's what we've been doing, decimal to binary. That's what we want to do. Okay, so how do we do that? I don't know. So we can use Python. That's one way to do it. And so there is actually a bin command where you can put in a number and you can print it out. So bin doesn't convert the number from into well, I should say it does actually do it, but let me explain exactly what it's doing. It's making a string out of a number, right, so that it can be printed. So notice here that this converts it to binary. But remember that a computer doesn't really understand the difference, right, between the binary of 42 and the decimal of 42, because it stores everything as binary. So how did it know, right, to keep it binary this time? And the answer is that this is actually not a number anymore. If you print out the type of bin of number, then what you're going to get is it's a string, right? So it's actually a string, not a number anymore. Okay? So if you want to keep it as a number, that's one thing. If you actually want to know what it is in binary, you have to convert it to binary, and bin does that, but it doesn't give you a quote-unquote number anymore. It actually gives you a string, right? Because computers don't really understand, right, decimal anyway. So that's basically that. It's going to be very rare that you're going to have to... we usually forbid bin, and I'm not sure that I'm going to keep it forbidden. I might allow you to use it, but it's so rare that I don't have any particular homework problems or anything where it actually helps you to use it. It's just something that if you ever need to convert a number into binary, it's allowed. So don't put type in anything though, right? Type is a technically forbidden keyword, so but I'm allowed to use it. Sorry for all those caps. Sorry, not sorry, right? Okay, cool. So let's use Python. Okay, we did that. But I guess your question, when you're a programmer or a mathematician or... Yeah, exactly. But how does Python do that? Right, so that's a good question. Here's the algorithm. And then we'll type it up into Python and run it. The conversion algorithm basically goes like this. You start with a number, right? And that number is going to be in decimal because pretend, right? Then what you do, okay, is you're going to divide, or I'm sorry. The first thing you're going to do is you're going to go while the current number is not equal to 0, and then you're going to say, current equals to number, basically. And then what you'll say is that if current mod 2, right? So if it's odd, then what we're going to do is add a 1 to the binary expression. Okay? Else, we're going to add a 0 to the binary expression. And this is really a string, right? And then the last thing we're going to do is we're going to move up to the next space. So this gets us the bit, right? Gets the current bit. And then the next thing we're going to do is move up one place. And so how do you move up one place? Well, how do you do that with a decimal number, right? In order to move up one place in, say, 532,817, you divide by 10, so that now you ignore the remainder, so that what you end up with is 53,281, right? And then you divide by 10 again to get to the next place, divide by 10 again, divide by 10 again, and each time, right, you already have dropped the actual value, the actual bit, so you don't care about the bit anymore. You've already recorded that. So what you get to do here is you basically say current divided equals 2. Okay? So let's write this up in Python. Yes, I am. I'm doing integer division, right? Just because I want to drop the remainder, right? It's important though, right? Because if I were doing regular division, then it might turn out to be a float. Don't want floats. No, floats are no good. Just integers, okay? So let's write this up in Python, and basically it's exactly this algorithm, except this and this require just a little bit of thinking. So I'm going to do it wrong first, and I want to show you what happens when you do it backwards, and then we'll fix it and do it right. So I'll do it the obvious way. Let's say decimal to binary. So this is like and then here's our number, right? So what we're going to do is we're going to write a little while loop, while number. And then what we're going to say is, let's see, result is equal to empty string. Okay. Actually, let's make it 0b so that at least there's something. Now there's a few edge cases that we'll have to deal with here, right? Because what if the number is actually equal to 0? So if number is equal to 0, or if, I guess, as a more, if not number, it always rounds down, and that's what I want. I always want it to round down. I do not want any remainders. I want it to take the remainder and get rid of it. Okay. So this is a little what people call an edge case, where what if the number is just 0? Then let's add a 0 to the 0b and we're done. Okay. Now, what if it's not just 0? Then here's what we do. If number mod 2, right? And remember what number mod 2 does. If number mod 2 is not equal to 0, then it's true. So if number mod 2, then what I'm going to do is I'm going to do result plus equals 1, else result plus equals 0. Now this is wrong, but we'll fix that in just a second. Unfortunately, this is kind of the obvious thing that you want to do, but I'll show you why it doesn't work, and I'll show you how to fix it. Okay, and then what you do is you do number divided equals 2. And then you will return, I'm sorry, yes, that's right, result. Okay, so let's do this a little bit, okay? And we'll see what happens. So let's print out decimal to binary on 5. And of course, this one is going to actually work, and you might see why. So you see that this one works, 101. But what if we do something like 6, right? So 6 is 110, right? Because it's 4 plus 2. But let's see what pops out here. Oh, weird, right? Uh-oh. It's backwards, right? What we've been doing is we've been slamming on the bits onto the end, not onto the start, right? We need this 0 to be here, we need this 1 to be where it is actually, and then this 1 needs to be... So everything is flipped, right? So how do we fix this? So, good question, right? How do we fix this? Well, so this thing, remember what plus equals does. It says result is equal to result plus 1 in this case, right? That's what result plus equals 1 means. Right? So we don't actually want that. We want to flip it around. And what we want is result is equal to 1 plus result. Unfortunately, you can't use plus equals here. Right? It just doesn't work because it doesn't give you the right ordering of putting the strings together. So you can do this though. 1 plus result. And then here we'll do 0 plus result. And basically this is going to work, except I think what it's going to do is it's going to slam on the 0b at the end. And it does. So let's fix that too. So instead of putting 0b on at the beginning, we'll just put 0b on at the end. And we'll make this an empty string. So now now it's fixed, right? And so here we go. Let's run this thing. So now, what have I done? Why is this not? So 5 is 101. Thank you. Thank you. I didn't delete that. Oh my goodness, that. I was gonna stare. I was gonna stare at that for 10 minutes. I would never have seen that. Well, by never I mean it would have taken me about 10 minutes to see that. Thank you, everybody. Yeah, that plus equals. Whew, right? That would have got me. So, okay, cool. Here we go. There, that's better. I was like, wait, what? I'll admit it. Can I admit it? I was confused. I really did not understand what was happening. I was like, but this is the algorithm. I was like, how did this is wrong? So, anyway. Okay. So, here's the thing, right? It might look like this is an algorithm that is hard. Well, I wouldn't say that. But it might look like, oh, hey, at least we have computers to do this. And yes, you do. But notice something about this algorithm, right? You just go while the number isn't 0. If the number is odd, you add a 1 to the front. Else you add a 0 and you divide by 2. We can actually do this one by hand, right? So the good news here is that, like, this... okay. Right, so we can... Now, let's convert, say, 532... Well, okay. 532,874 into binary and see what happens. And here you go. Here's binary of 532,874. So obviously here, you're like, I don't want to read this. That is horrible. Okay, I agree. But, so our algorithm works, right? Let's do 42 just to prove that it gives us the right thing. Yep, it gives us the right thing. Let's do 511 just to show that it gets us, what is it, 9 ones in a row, I think. This should be 9 ones. That's 1, 2, 3, 4, 5, 6, 7, 8, 9. Yep. And we're not going to check this number because, as I say, like, right? This is just a big thing that's unpleasant to look at. So whatever. Anyway, okay, so let's do a few of these by hand, right? So I think that's kind of good if we just do a few of these by hand. So let's do a few by hand to prove that it's not impossible to do these by hand. Of course, you know we're in CS, so that means we'll use a computer because we're not living in the 1880s, but that's right. That's exactly right. And let me show you how this works. So let's convert a number. Let's convert, say, 483 in decimal into binary. Right? 483 decimal into binary. So, how do we do this? Well, let's use the algorithm, right? So the algorithm says, is the number odd? If so, if yes, add a 1. I don't mean add a 1. I mean put a 1 at the start, else 0, and then divide by 2. Right? And repeat this until number is 0. Okay? So let's do this process. So the first thing we're going to say is the number is odd. So 483 is odd. So yes, our first thing is going to be 0b something 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 1. And now we're going to divide by 2. And I'm going to use a calculator just to make sure, even though it's what? 241? Yeah, 241. And you might say, but it's 241.5. And I say, integer division, right? Integer division. No remainders. Okay? So, cool. Now, is this odd? The answer is yes, it's odd. Add a 1. Divide by 2. What is 241 divided by 2? I guess that's 120.5. Am I right? And by am I right, I mean, I think I'm pretty much right. So what we're going to get is, now you would say, so you would say odd. And here we'll say odd. I don't know why I keep saying PDD, but even. Even. So now we're going to get 0, 1, 1. So I add the question marks to indicate we're not done yet. 0, 1, 1. Okay, now we divide by 2. 60, right? Even. 0b. Question, question, questions, question. 0, 0, 1, 1, right? Cool. Well, I didn't teach you this back in high school because I wasn't your math teacher in high school. You see? And then we divide by 2 again. So we got a bunch of zeros. Fine. Now we divide by 2 again. It's not 16, it's 15. That was a typo. Don't believe. Hey, I mean, I taught calculus for like 10 years, right? So, I mean, I could have been your math teacher at some point, but just you would have had to go to UMD and take calculus a few years ago. Anyway. Wait, 15 isn't even. $15 is odd. So we get 1, 0, 0, 0, 1, 1. And now we divide by 2 again. We'll get 7.5, round down, as you say. Odd. And then we get 0b. Question, question. I guess. Okay. I think we're almost there. 1, 1, 0, 0, 0, 1, 1. And now we just have to basically deal with 7. So 7 divided by 2 is, what? 7 divided by 2 is 3. Zero B. Divide by 2, we get 1, which is odd. And at this point, we're almost done, right? So, question mark 1, 1, 1, 1, 0, 0, 0, 1, 1. And finally, you divide by 2. And now remember, it does matter for, well, actually, technically, it doesn't matter for us. Right, repeat until the number is 0, but 0 is even. So, technically, you could either just do this and say, I'm done, or you can say this with a 0 in front, right? They're both the same. Okay, now let's check our work with Python, right? So I claim that 0b, 4 1s, 3 0s, 2 1s is equal to 483. Is that true, right? Let's check it, because you should never believe anything that I say. Okay, you should believe this, though, right? So that's true. All right. Yeah, it's I'm not going to say that it's a, quick process. I mean, it would be a quicker process if we were to, say, convert, say, 17 into binary, right? If we converted 17 into binary, then let's do this. So 17 is odd, so that's 0b with a 1. Right? Divide by 2, so we'll get 8, which is even. So you get 0b, question, 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 0, 1, right? Then you divide by 2, you'll get 4, which is even. 0b, question, question. I think I need some more questions. I'll put some more question marks. You don't have to get the number of question marks right. I'm just trying. Now we're safe. Plenty of question marks. So now what we're going to do is it's even, so 0, 0, 1. Now you get 2, which is even again. 0b question question. 0, 0, 0, 1. And then you divide 1, right? Even. Wait. 1 is odd. 0b. And then question mark 1, 0, 0, 1. And so, as I say, you don't have to do this last step. Once you get to a 1, you basically know you're done. On the other hand, you are permitted, you are not forbidden to do divided by 2 and say even 0b 0, 1. And the reason for this is because if you check and you print out, say, this versus this, right? The point is that it doesn't make a difference, so they're both 17. Now, of course, you might have been able to say, I could have just done that in my head, right? Because I know that 16 plus 1 is equal to 17, and 16 is equal to 2 to the 4th power. Yep, I agree. So what you can do is you can just say this is 1, and then a bunch of zeros, 1, right? Because remember, this is the 0's place, 1's place, 2's place, 3's place, and 4's place. What's going on? I don't even completely understand. Okay. Yeah, I mean, so there's a little Futurama joke, right? Let me see if I can find it. Let's see, is my desktop audio on? I think so. I don't think it's on. That's unfortunate. Anyway, I'll just post the link so all of you can, watch it properly. Okay, that's better than messing with OBS and fixing it. Yeah. So, there you go. All right. Let's do maybe 2 more of these. Wow. So what I will say is that sometimes binary is written as 0b and then your number, so, and sometimes it's written just with like b at the end, and I think there are some versions of assembly language that do it the second way. Sometimes you'll see it in textbooks. But basically, if you see a B, what that usually means is that it's in binary. The other thing that you might see occasionally, very rarely, in CS, but more commonly in math, is you'll see something like with a subscript 2. Right? Because if I just write down a number for you, and I'm just like, right, what is this number? Is this, I guess, what, 10,101,010, or is it this number in binary, which is actually what, right? 2, 8, 32, 128. So it's something in the 256-ish range, right? So And the answer is you wouldn't know, you don't know, unless someone says. And so most textbooks are going to have some kind of subscript, or they might have a suffix of B on the end, or maybe they'll even put it at the front, but I haven't seen that too much. Normally if they're going to put it at the front, they put the 0B at the front. Yep. This is not really, I'm not going to be, I guess I'll have to cover all this just because in case I accidentally write one or the other version, I want you to be aware that like any potential thing like this means the same thing. And we're not trying to trick you, it's just me writing it in one notation or the other notation and just forgetting. But yeah, Python and C++ do the 0B stuff. Okay. Yeah, if you don't see a B, then you should consider it as decimal, right? Because basically, by default, we do decimal, right? And that's the same thing that you've been doing in Python. Okay, cool. So, yep, let's do one more conversion, right? Let's convert, say, 87 into binary. I was like, convert 87 into decimal. I'm like, okay, done. Okay, let's convert 87 into binary. So 87 in decimal, right, is odd. So I'm just going to write a 1 here. I'm not going to write all the 0B stuff until the very end. We divide this by 2. What do we get? I guess we get 43, which is odd. 1, 1. Divide that by 2, we get 21, odd, 1, 1, 1. Divide that by 2, we're going to get 10, even. So then we're going to get is 0, 1, 1, 1. But remember that this leading 0 is not, it's not just a 0 yet, right? It actually matters. You have to keep this 0 in because when we divide by 2, we're going to get 5, which is odd. So then what you're going to do is say 1, 0, 1, 1, 1, right? And you needed that 0 in there. You can't just drop it. Divide by 2, we'll get 2, which is even. So 0, 1, 0, 1, 1, 1. And then finally 1, which is 1, 0, 1, 0, 1, 1, 1. And then if you really care, you can just put a B on the end. So let's double check that this is 87, right? Nope. It's always easier to go from hex to binary and binary to hex than it is to do any one of those to decimal. And I'll explain why in just a second. So, okay, let's talk about hex now. Oh, and it is 87, so, not wrong. Okay, so let's talk about hex. So when we say hex, what we really mean is hexadecimal. And what this means is, it's really, the hex means 6 and the decimal means 10, so it's like 6 plus 10 is equal to 16, which is the base. And the cool thing about base 16 is that it's easily convertible from base 2 to base 16, and I'll show you that in just a little bit. But first, we need to deal with a problem, a big problem, medium-sized problem, right? Medium-sized problem. So remember what we were doing when we created binary. When we created binary, a bit was just 0 and 1, and we have digits, right? We have digits we can steal to represent the binary 0 and 1 bits, right? But for hex, remember it's base 16, so let's count, right? So the hexits, or whatever, you call them hexadecimal digits, which is kind of a mouthful. I mean, I wish we could call them like hexets or something, but I don't. That's not an accepted piece of terminology. So, so basically, let's count. We go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. You know, you might be tempted, oh, just write 10. But what's the problem with 10, right? 10 is a problem because it's it's actually 2 digits, right? It's 2 symbols. So no good. Yeah, you're spoiling all the fun. So the way we usually do it in programming, and it's a pretty universally accepted standard, is that 10 is equal to A. And then we just start counting in the alphabet. So we say B is equal to 11, C is equal to 12, D is equal to 13, and E is equal to 14, and finally F is equal to 15. Now remember. So remember, what do you have to remember? You have to remember that there's no 16, right? Because 16 in hex is 10H, or really you might do... So the way to write hex usually in most programming languages is 0x10. So this is 16 in decimal. This is 10 hex. So you see people all the time abusing the language of decimal into hex. So you always want to be careful. If someone says 10 in hex, right, and they clearly just mean 10 in hex, that's fine. But if your life depends on it, you might want to ask, is it 0x10 or is it 0xa, right? Because A is the number 10, right? And this is the symbol 10, right? Which is really 16, right? So if your life ever depends on it, make sure you ask what people mean, because there is a lot of abusive notation going on here. Okay, so cool. All right, so how do you represent a number? So here's the cool thing about the conversion between binary and hex, okay? The cool thing between binary and hex is that 4 bits are always equal to 1 hex digit. And so what we can do is we can actually do something like this. So let's do it like this. So what are all the possible... Here's 0000, 0001, 0002. Oh wait, no, that's not right. 010. Let's count in binary. 0011, that's 3. And then how do you count up? You add 1 to this, so then it becomes 0100, that's 4. And so then what you're going to get here is 0101, that's 5. You'll get 0110, that's 6. 0111, that's 7. 1000, right? That's 8. 1001, that's 9. And then here we go. 1010, that's 10 or A. And then 1011, that's 11 or B. 1100, that's 12. 1101. And, well, not finally, 1110, and then finally F, 1111. So, why isn't it H? I don't know. Tradition. So let's make a little chart. So this is, I'm just making a little chart here so that we can have all the possibilities, right? this one. Whoops. And then finally, here we go. So here's how hex works, right? This is equal to 0, right? This is always equal to 1, 2, 3, 4, 5, 6, 7, right? And this is not very exciting yet. 8, 9, A, B, C, D, E, F. Okay? So that's how this works, right? So now, at this point, basically, you can convert from binary to hex and hex to binary just using this chart. Nothing else, right? So let's do that, right? Let's do some conversions. So let's say we have the binary number 1101 space. I'm just going to space 1001 0111 01 0000 1111 1. I don't know. I'm just kind of randomly doing things and saying zeros and ones, so I should stop saying things. Okay, so this is a horrible binary number. It's extraordinarily long. There's actually a little technical term for what these are. So 4 bits are called a nibble. And that is absolutely trivia. That will not be tested, but it's cute, right? Because you can say 4 bits are a nibble, 2 nibbles are equal to 1 byte, right? Which is 8 bits. What happens if it can't be split up? So let's do an example where it can't be split up. So let's say that you just have an extra 2 ones here, like this. The answer is just put some extra zeros on the beginning. So if you can't split your number evenly, just kind of put extra zeros at the front until it does. So, okay, let's convert now. So this is binary, so let's put a 0x here to convert it to hex. Well, so how do you know if you're reading a 4-bit chunk? Because these are 4 bits at a time. So, okay, let's convert from the back up. So this is what? I think this is E, right? Which is 14. And then this is what? D. And then 5, F, 0, 5 again. 1001 is, I think, 9, right? 1101, D. And 0011 is 3. And that's it. We're done. So that's how to convert these numbers, right? So it's pretty horrible, but that's it. All right, so let's check to see what the heck this is, right? Let's copy paste it, delete all these spaces. There we go. Delete. Okay, let's see what this number is. This number is that. And so now let's print out this number. And just hopefully it's the same, because if I've made a mistake, then it won't be. But if I haven't made a mistake, then it might be. Didn't make a mistake. There we go. So we see here that converting from binary to hex and hex to binary is really just using this chart, right? And now, I mean, this chart is something that you can rederive. So there's nothing, I'm going to say, like, there's not really anything to memorize here. But at least when we used to do this stuff, I don't know where the terms came from. I mean, bit definitely came from the fact that it's a binary digit, right? So that was done by mathematicians. If you ask where did the term nibble come from, that was definitely computer scientists. If you ask where the term byte came from, also definitely computer scientists. Probably sometime between 1940 and 1970, somewhere in there. I don't actually know the etymology of these terms. But yeah, no, You have to blame the computer scientists for the yeah. I mean, I think it's basically because everything is a bit, and then I'm not sure if nibble was invented first or byte. Probably byte. So I imagine maybe the term byte came around in like maybe the 1970s, because I would think so. There was a long, so now everything is in bytes, right? ASCII stores everything in bytes. Everything. Oh, how would you make the algorithm for hex? You mean hex to decimal or decimal to hex or something like that? Anyway, okay, so let's do one more example. So let's convert, say, into binary. And so to do this, let's just do this. So we know that 3 is 0011. I know that 2 is 0010. I know that A is 10, so that's 1010. And then 4 is 0110. Nope, that's 6. 0100. I both said and wrote the wrong thing initially, but yeah, 0100, yes. And so then let's do another example, right? Because this is quick. Actually, no, we don't have time for that. Let's do the conversion algorithm. So how to convert from, say, decimal to hex, right? That's a good question. And then maybe we'll talk about hex to decimal, but decimal to hex is a good question. So as it turns out, it's the same algorithm, right, as here. Where is this algorithm? It's the same thing as here, okay? Except the only thing we have to change is we do the number, instead of doing current divided by 2, we do current divided by 16, and we do current mod 16. And so instead of adding 1 or 0, we add the hexadecimal digit to the front of the number. So let's write the algorithm. Let's do that in Python. So let's do decimal, right? We're stealing this algorithm almost purely, right? So it's not decimal to binary anymore, decimal to hex. And so we're going to mod it by, what we're actually going to do is say, if the number mod 16 is less than or equal to 9, then what we're going to do is do the string of number mod 16, right? Like that. Elif, I mean, let's just do it in the silliest possible way. If it's equal to 10, then we're going to do A, right? This is not the best way to write this, but B, C, D, E, F, okay. F, E, D, C, B, so, and then we change this to 11, 12, 13, 14, and 15. Now, of course, you might say, but wait, you know, that you can't possibly expect me to think that this is good, and I don't. But this will do. Okay. Oh, and we should, instead of doing 0b, we can do 0x. The other thing you should say is that I can't believe that you would actually have to write this function, and the answer is there is actually a hex function, right? So if you do 32,921 and you print out the hex of it, then that will give you the hexadecimal of that number. So let's see what happens. So I guess it's 0x, 8099. So let's test our own function here. So let's print out, say, decimal to hex of the same number, 32,921, and let's just, hopefully, I mean, we didn't, I guess this is why you test your functions, right? This is why you actually test your code. I haven't really tested this yet, so we don't know if it'll work. It seems to sort of work. let's do the hex of, say, 84. Yeah, 84. Does the hex function work on binary? So remember that this number is just a raw number that comes in. Now we're pretending that it's decimal, but really, like, any number that gets fed into this function, like if you feed in a number, say like hex of 0b, something like this, and you do something like this, remember that the computer doesn't know, once it passes this in as a number, it doesn't know whether the original thing was hex or binary or decimal. All it knows is that it's been converted to binary because it's storing it inside of its memory. So you see here, it's going to do the same thing. So this sort of converts from binary to hex, but what it's really doing is just, here we're pretending as if this is a decimal number, right? So, yep. Decimal to hex of 3. Let's prove that it just gives us 0x3, right? In fact, let's just for I in range 255, or let's make it 256. Decimal to hex of I. Let's just print them all out. There we go. So we see here that there's a difference between their hex function and our hex function. It doesn't make either one of us wrong, but if you notice, the default Python one uses lowercase letters and we use uppercase letters. Is there a difference? The answer is no. You notice that Python will allow you to do 0xabcd, right? And you can also do 0xabcd. And those are both hex numbers. They're both the same hex number. There's no distinction between upper and lower case in the hex. So you're allowed to do either one. Old style coding, like the old style, you see this mostly in like C, is all upper, right? They're always uppercasing everything. In more modern languages with, what do we call it? Kind of like less uppercasey style, you'll see a lot of lowercase stuff. But again, it really does, it's just totally irrelevant. But Python doesn't care. Python accepts both. Okay, so I guess we still have to do a little bit more. Well, we'll do some actual. So we've written down the algorithm here, which is, you know, not great. But actually, next time what I'm going to do is, so next time on CMSC 201, what we'll do is we will calculate using this algorithm by hand, right? So I want to do a few decimal to hex and hex to decimal calculations by hand, because yes, our algorithm works, so you could trace through how this code works, but I think the right way to do it is to understand the actual algorithm, and then what you do is you just kind of, like, this code here is based completely on the algorithm that you can do by hand, right? So this is just automating what you would otherwise do by hand. This is not doing anything special. So we're going to calculate decimal to hex. And so remember that to do binary to hex or hex to binary, you just use the chart. And to do binary to decimal, you do the powers calculation, right? And to do decimal to hex, decimal to binary, you need this algorithm, right? The basically mod, we can even call it like the mod divide algorithm, right? Because that's what it's really doing. It's just modding by the base, dividing by the base. Modding by the base, dividing by the base. Yep, so it's totally possible. There's and just the only thing to say to finish up this class is that there are, you know, why did we pick 2, 10, and 16, right? Right, we picked base is equal to 2, 10, and 16, but why? Why didn't we pick all the other possible bases? 3, 4, 5, 6, right? 7, 8, 243, right? It's possible to have all these other bases. Why not? And the answer is basically that For computers, remember, they do things in on-off. So on-off really lends itself to base 2, right? Lends itself to binary. So that's why we do that. So then the question is, why hex, right? And the answer is because it's really just a shorthand for binary, right? That's the whole point of hex. Hex allows us to shrink those just absolutely large binary statements into smaller statements, just smaller expressions. That's the whole point of hex. If binary was compact, which it can't really be because it's base 2, but if you could make binary more compact, well, then you would be making hex, but that's the point, right? So that's why we use hex. And so there's actually another thing that you might see occasionally, which is called octal, which is base 8. And we don't really teach that in this class, but it works exactly the same way as base 2, base 8, base 10. And of course you might ask, well, what's up with base 10 then? And the answer is, well, you've gone through, say, 12 years of schooling where that was the base, right? It was all the base that exists. So, so basically base 10 is the one that's human understandable, and base 2 is computer understandable. And base, technically octal, but mostly hex. You don't see a lot of octal anymore, but mostly hex is, we'll call it human, sorta, computer, definitely understandable. Right? It's kind of, base 16 is kind of like the compromise between what humans can read, because if we just give you some like 32-bit thing, which is just this horribly long, binary expression, it's kind of hard to look at that, right? Because you have to like separate it first, and then you have to think to yourself like, okay, now I have to start counting all these powers. It's just a huge, undertaking to look at that number, right? It makes you feel tired to even look at it. And so that's why we do hex, right? Hex allows us to shrink this into 1, 2, 3, 4, 5, 6, 7, 8 blocks, 8 digits, or really, 8 hexets. And so that's the other reason why sometimes they write binary in these 4-bit combinations, right? These little nibbles, is because one nibble turns into one hexadecimal digit. Anyway, so that's basically it. And so yeah, we'll finish up, and we'll do some more of this next time. But yeah, basically, I'll release this PDF because I think it has everything you need to kind of get yourself started. Yeah, hexets. I do like the idea of hexets. I really want that to be a thing. Unfortunately, all I ever hear is hexadecimal digit. But it feels long, and then you use the term digit, which means 10 again. So you don't want to, you should tend to avoid that. Who cares? Anyway, so it's all a bunch of notational garbage, but I wouldn't worry too much about that because, that's not the point. The point is, can you convert from decimal into binary, binary into decimal? And then can you use the shorthand, which is hex? Can you convert back and forth between hex and binary? Yes. Here's a chart. Can you convert back and forth between... so one thing you can always do if you want to know how to convert to decimal or whatever, you can always convert into binary and then convert from there to decimal. That's one option. But I'll show you how to convert from hex straight into decimal next time. All right. That's all for today. I'll see you guys... Wait, today's Wednesday, so I won't see you guys Wednesday because today's Wednesday. I'll see you guys next Monday. That's what's going to happen. So I'm going to read the only last thing I know I'm using way too much time. Last thing. Project 1 will come out either probably Friday night, maybe Saturday morning. And it's going to be Mancala. If you've ever played that. I might do a little bit of a little video with TAs doing a little example of what the rules are of the game, and I'll post a bunch of YouTube videos, short ones of how to play the game just so that you understand. And I'll be coding up all of the graphical stuff so that you don't have to worry about that. All right. That is really it. We are done. Absolutely finished. Completely completed. All right. See you guys.